In this lesson, we will be learning everything about tensors in machine learning. Tensors are core concept. We will be using this MIT licensed open source material. The creator of this Colab notebook and material is Antonio Norelli. Here is his information. Click the link below to access this Jupyter notebook, and then you're gonna scroll a bit down to this cell. If you want to get personal help from our instructors that will help you with these and all of our topics in machine learning and AI, click to the link in the description. You're going to get access to all of our courses from beginner, intermediate, advanced, building LLM, stable diffusion from scratch, etc. The course building is still in progress, so it's going to be a lot cheaper for you to join now, and you can learn together in our community from our instructors, make posts, ask questions in comments, etc. First, we are going to import NumPy as NP by running this cell. Then we are going to also import Torch, which is PyTorch, and let me just exit this for a moment, and then we are going to display the Torch version. We can see that we have CUDA, which is GPU support. So we can do calculations on the GPU as well. And GPU is a lot better than CPU for parallel processing if you have a lot of simple tasks, while CPU is better for complex tasks. But CPU will execute tasks one by one and not parallelly like GPU. Let's run this cell below to create our first tensor. So the command is torch.tensor, and then we specify inside of the brackets, we give the kind of array specifications. So this is array of two arrays. This array has these values, this array has these values. Data type will be torch.integer32. So this is our matrix or our tensor, two-dimensional tensor. Torch.zeros will give us basically a tensor of all zeros, and we specify the dimension as a tuple. We can also define torch.ones, and then the dimensions and data type is optional. We can say float 64, for example. And then we're gonna get all of the ones with these dimensions. If we say torch.I, we are going to get identity matrix. This I is just a play on the letter I that represents identity matrix. We can also create a tensor of random numbers by saying torch.rand and then specifying the dimensions. Here we can see that we got 2 by 2 matrix. The question says from which distribution these random numbers are sampled. Check the PyTorch documentation. You can go ahead and I will reveal the answer right now. So they are specified from distribution 0 to 1. 0 is inclusive, 1 is exclusive, so the value can be 0, but it cannot be 1. We can also use torch.randint, and then we can specify from which integer to which integer, and then the dimensions of the matrix. So this one is going to be inclusive, and this will be exclusive, so the random integer cannot be 100, but it can be 0. Here we are going to create a tensor filled with random values, 3 by 3 tensor, and assign it to to variable t. And then we're gonna create a new tensor. We're gonna say torch.ones like, and then pass in t. This will create a tensor of all ones with the dimensions of t, so 3 by 3. Now we're gonna learn how to convert from PyTorch tensors to NumPy arrays. So we can say t is equal to torch.rand, and then we're gonna define 3 by 3 tensor of random numbers, and then type is gonna be float 32. And then if we just call NumPy function on this tensor, it's going to be converted to the NumPy array. So torch tensors have this NumPy function inside of them that you can call. There are many other functions available to create tensors. Exercise: create a matrix M belongs to real numbers 3 times 3 that is filled with 2 along the diagonal and 1 elsewhere. That is Mij has value of 2 if I is equal to j, and has value of 1 otherwise. You're going to write your code here. You can use ChatGPT. You can ask it how to do this, maybe get some hints. And then I'm going to reveal this solution. So you can do this with like if loops and stuff, but this is a simple way to use just torch functions. So you're gonna create torch.ones 3 by 3. It's gonna be filled with ones completely, and then just add another tensor, torch.I, which has dimension of 3. So you're gonna add another tensor that has everywhere zeros except 1 on the diagonal. So it's gonna have 2 on the diagonal. The type of a tensor is the type of each element contained in the tensor. So if we say tensor is equal to torch.random 3 times 3 dimensions, and if we print t.d type, we're gonna get the data type of this tensor, which is torch.float32. So t.shape is going to be the shape of the tensor. We are going to define shape of the tensor as a tuple of numbers, so it can be 2, 3, and infinitely many numbers. This tensor is going to be a matrix with 3 and 5 dimensions. And then if we print t.shape, we're gonna get torch.size, and then this is the shape of the tensor. The device of the tensor indicates the memory in which the tensor currently resides. RAM denoted as CPU and GPU memory denoted as CUDA. If we say t.device, we're gonna get CPU, for example. As I said, you actually want all of your tensors to operate on GPU because there is no big drawbacks to that. Usually you want them on GPU, but GPUs are a bit more resource intensive and more expensive to operate on. Let's see another exercise. Given a matrix X belongs to R m times n, create another matrix Y that belongs to R m times 3 filled with ones using X. And we have X is equal to torch.random with 100 times 42 dimensions. So the task is to, whatever the dimension of X is, Y has to have the same first X dimension, and then it should be always filled with ones. I'm going to reveal the solution in a few seconds, so let's reveal it. You have torch.ones, and then the first dimension is going to be x.shape, but the first dimension of the shape, because as you remember, shape is going to return array of dimensions. So we want the first dimension, and then the other one is going to be 3. For now, we've been using this on CPUs, and we are going to move this code onto GPUs, so it's going to be a lot faster. The first thing we will do is we will see torch.CUDA.is available, and if CUDA is available, which is basically GPU, and it says true, then we can move it to GPU. The way you would move your code to GPU is as follows. Device is equal to, so first you're going to specify the device you're going to be using. It's going to be torch.device and then CUDA, string CUDA, if torch.CUDA is available. In this case it is, else it's going to be CPU. And now we can see that if we print the device, device is going to be CUDA. Now this is only the variable that contains our device, but we have not moved it yet. So we are going to create a new tensor, torch.rand 3 by 3, and then we're going to say t is equal to t.to and then device. We are going to reassign the variable. You need to reassign the variable, and then we're going to just add, you're going to call the function to that these torch tensors have, and then give it to what device to move it to. We don't actually need to first construct the tensors onto the CPU and move it to GPU. We can also construct tensors directly on the GPU. So we can say t is equal to torch.ones, and then device is going to be equal to CUDA. Another way, if we have a tensor, we can also say t is equal to t.CUDA. We can call the function CUDA. The problem here is that the CUDA will not run if GPU is not available. So you don't want to hard code it like this, or you want to be careful. You want to actually use this method. We can skip a little bit down. We don't need to learn this. We're going to go to tensor rank. Now we are going to learn about tensor ranks. So rank 0 tensor is just a scalar. So if we define torch.tensor, we pass in value 3. This is just going to be a tensor that's actually just a variable with value 3, just a scalar. We're going to print this tensor, and then this print underline array, this is basically our function that we defined earlier. I said we can skip this, but basically it's just going to print the tensor in a specific way. So it's going to say this is the tensor and this is the data type, and then we're going to also print the size, and then this data type here is the same data type as this one. It's just a different way of printing the tensor that we defined ourselves. And then we can actually, if we call t0.item, we're going to convert this t0 tensor into the same float 64 type, but it's going to be Python based, not Torch based. So if we print item and type of item, it's going to be 3.0. This is the scalar, and then the float. This will be base Python float type. Be careful, non-scalar tensors cannot be converted with an item call. So we're going to try x is equal to torch.ones 3, so we have 3 by 3 ones matrix. We're going to call item, and then it's going to throw an exception, and we're going to print the error. So the error is going to be only one element tensors can be converted to Python scalars. So rank 1 tensors of length n have a shape of n. Also notice how this is still a tuple and there is no second number. This is the shape of rank 1 tensors, which are basically same as Python arrays. So we're going to create a tensor t1 is equal to torch.tensor, and then this is just passing the array. And then if we print our tensor, we see that this is our tensor. The shape is going to be 3 because it has 3 elements, and then the data type is going to be integer 64 because we haven't specified other data type explicitly. This is the default. We can also create a rank 1 array with a single scalar, so we can just pass in array with one element. This is still rank 1 because this is an array. It's not rank 0 because this is not a scalar. I said you can only call item function on rank 0 tensors, which are basically a scalar, but PyTorch and NumPy are going to figure out that if you have array of just one number, they're going to figure out what you're trying to do, and they're going to convert it to the Python scalar. Rank 2 tensor have shape n, m, so it's a tuple, and it's important to also see that rank k tensor have shape n1, etc. to nk, so it's a tuple of numbers. And that's why, in order to keep this consistent, for rank 1 shape, we're going to also give it a tuple of the dimension, and then comma, and then empty space or nothing here. Just to keep it consistent, we don't want to just say like n without tuple, we want to keep everything in tuples. That's why PyTorch requires you to do this rank 1 tensor shape also in a tuple. If we take a look at our rank 2 tensor again, we're just going to, this is basically a matrix. So we're going to define a matrix, array of 2 arrays. And if we print it, we're going to see that this is a matrix. You see the shape and the data type. If you have a column vector, that's a rank 2 tensor. So our T1 tensor right here, it was 1, 2, 3 in an array. But if we convert that to a column tensor, and we're going to do that here, it's going to say T column is equal to T1.reshape, and this is how we can convert it to a column tensor. And then if we print it, it's going to be 3 times 1 matrix. Now let me explain this -1, 1 in these brackets. So we are going to create, we're going to reshape T1, and this dimension is going to be 1. So it's going to be, the inner dimension is going to be 1, and then with -1, we tell Torch to automatically then calculate the other dimension, that's going to be 3, based on what we have in T1. So this is going to be automatically calculated if this is 1. Rank k tensors have a shape from n to nk. If we say torch zeros, and then we give it this shape, it's going to be basically a tensor with this shape. So there is inner arrays, and then a bit outer arrays that group in 2, and then the big outer array. We can also say torch once, and then if we say 2, 2, 2, 2, we're gonna get 2 elements here, and then these arrays have 2 smaller arrays, and then these arrays have 2 these smaller arrays, and then big arrays have 2 of these inner arrays. Exercise: build a tensor x belongs to R k times k filled with zeros and the sequence 0 to k minus 1 along the diagonal. So this is what it should look like. It's filled with zeros, and then along the diagonal it goes 0, 1, 2. This should not be done with any functions. You just need to write the actual numbers with these kind of square brackets, and then inside square brackets, and then give it like what kind of numbers, and then what kind of, just to get this tensor as output. And I'm going to show the solution. Torch.tensor, and then we're going to create this tensor. It's going to display this tensor. Exercise: what is the shape of the following tensor? Okay, you can pause the video, but I will explain. So we start from the innermost array. So we have 3 elements here. So the shape, I'm going to say here, I'm going to get some code. So the shape, we have this. It's going to be 3 at the right side. And then before 3, we're going to have 2 of these. So it's going to be 2. And then we looked at these outer brackets, and then we're going to look at these completely outer brackets, and they have 1, 2, 3, 4 elements. They go in the beginning. So it's going to be 4, 2, and 3. And if we go ahead, so here I wrote the solution. If we generate torch.once with this shape, we're going to get the same tensor. I had to import torch because I'm running this whole notebook again, but if you already imported torch before, you don't need to import it. Changing and adding dimensions. We are going to take a look at transpose dimensions. So if we have tensor A, we say torch.once, we define this tensor, and then we can say we choose the first row and the last column, and then we set it to 0. So this is the first row, this is the last column right here. We set that to 0. -1 means last. And now we can say A.T is going to transpose this matrix. So you see where 0 is, it's going to be right here. First element in the last row. But be careful, because we have not assigned, we just wrote the transposed version of A, but we did not say A is equal to A transpose, so A is going to still remain this tensor. We can also swap specific dimensions. So A.transpose 1 and 0 is going to swap dimensions 0 and 1. But this tensor already has only 2 dimensions. This is the first dimension 0, and the second dimension or dimension 1. And then if it swap these 2 dimensions, we're basically going to get the same as A.T. We can also use torch.einsum, which is Einstein summation, to do the same transposing. So we can just give it this note. Ij goes to ji of tensor A. So this is going to transpose the tensor A in the same way. Einsum is actually extremely versatile and important, so we are going to learn a lot more about Einsum, and we can do any kinds of operations with that. We can actually transpose just specific dimensions. So if we have a tensor of 2, 3, and 6 dimensions, and then I'm going to just set this number to 42, it's right here. And then if I say transpose dimension number 2 and dimension number 1, basically we're going to go from ijk to ikj. We're going to swap jk and kj dimensions. So the outermost brackets, dimension 0, is still going to have 2 elements. That dimension will not change. It has this element, and then here we'll also have this element and this element, but then inner dimensions are going to get swapped. So what this will do is it's going to take this 1, 1, 1, and then put it here. It's going to take this 1, 1, 42, and then put it into this dimension like this, into the innermost dimension. As I explained, we can do the same with einsum, and einsum is a lot more versatile and better than using this, although in this case we can use A.transpose, but you should be really comfortable with using einsum because it's a lot more versatile and powerful. So here, if we say A is equal to np.arrange10, this is just going to be an array from 0 to 9. And then if we say that same thing, arrange 10, and then reshape, and the dimensions are 2 and 5, we're going to get a matrix like this. After that, if we say A.transpose and then 1, 0, we're going to swap the dimensions. So the first one is going to be 0, 5, so it's going to take 0 and 5 and put it into the first dimension, 1, 6, put it into second array, etc. And then if we say A.transpose 0, 1 again, it's going to just return to the previous state. We can do this in another way. We can also say torch.from numpy, so we're going to create a torch tensor from numpy array A, and then we're going to call this transpose function, and we are actually going to get the same results as here. We can do the same by using np.einsum ij to ji of a array, and we're going to get the same results. Einsum is almost platform independent. It works with PyTorch, NumPy, TensorFlow, JEX, and everything. Another important feature of reshaping a tensor into different dimensions, we need to make sure to preserve the same number of elements. -1 in one of the dimensions means figure it out. Transposing and reshaping are two fundamentally different operations. So we're going to create a torch tensor from 0 to 12 or to 11, because 12 is exclusive. And then we're going to reshape it to a tensor of 3 times 4. So we're going to get this kind of matrix 3 times 4. And then if we call transpose, then it's going to just transpose this to 0, 4, 8, 0, 4, 8, 1, 5, 9, 1, 5, 9, etc. But if we call reshape on this tensor, we're going to get a completely different thing. So it's not going to be like this. It's going to start cutting 0, 1, 2, 0, 1, 2, because the inner dimension is 3. The outer dimension is 4. It's going to say these 3, and then 3, 4, 5, and then 6, 7, 8, etc. So to explain reshaping again, if we have some tensor that's 2 by 2 matrix, it's going to first unroll this whole matrix. So it's going to put everything into one array, and it's going to go in this direction like this, and then it's going to see the shape that we want to have, so 4 by 3. So it's going to start from the innermost shape. It's going to have 3 numbers, and then 3 numbers, and then 3 numbers, and then 3 numbers. So now it organized it in groups of 3, and we can just, well, this is already organized. We can just write it like this so you can see what it looks like. So let's say we have the same array, the same tensor, and we want to reshape it to 2, 2, 3. So we're going to start with the right number. So we're going to divide this in arrays of 3 elements. So we're going to group them together, 3, 3, 3, 3. Then we're going to continue with this number. So we're going to group these 2 and these 2. So as you can see, these 2 are grouped in square brackets, and these 2 are grouped. And then we can just, because this is already finished, this is already grouped, we can just write it in this way, so you can see what it looks like. So basically, we have 3 numbers, and then we have 2 arrays of 3 numbers, and then we have 1, 2 of those. So it's 3 times 2 times 2. Let's see how it gets executed. So if we say A is equal to torch arrange 12, we're going to get from 0 to 11. And then we're going to say A.reshape 6, 2. So the inner are going to have 2 elements, and there is 6 of those. If we say reshape 2, 6, the inner is going to have 6 elements, and there will be 2 of these. If we say reshape 2, 2, 3, the inner is going to have 3 elements, then it's going to be 2 of those arrays, and then the outermost array is going to have 2 of those. 1, 2. Let's try something else. We're going to use try except block. So we're going to try to a.reshape 5 minus 1, and then it's going to throw an exception. So we're going to catch this exception and say error. Shape 5 minus 1 is invalid for type of size 12. Can you explain why? So if we have shape 5 as the outer, as one shape, one dimension, why can it not calculate the other dimension? Because if we divide 12 by 5, it's not a whole number, so we cannot have a whole dimension here. Okay, well, let's see how we can use minus 1. So if I say a.reshape 1 minus 1, that means that the innermost dimension will be calculated and there will be only 1. You see that there is only 1 pair of brackets, so it has only 1 element, although this is still 2-dimensional array, but it has 1 element in one dimension and 12 elements in the other dimension. I'm not sure if this is a bit confusing, but basically, if you see that this inner array has 12 elements, and then you consider this inner array as one element, it's an array, it's an element, you see that there is only one of those elements, inner arrays, in this outer array. If we say reshape to minus 1, 1, that means the innermost dimension has 1 element, and then we're going to have as many of those as necessary. It's going to be calculated, so we need to have 12 in the outer dimension. If we say a.reshape minus 1, we are just going to flatten the entire tensor, so whatever dimensions it has, everything is going to be put into one single dimension. So you can have 3 by 5 by 10, and all of the elements are just going to get flattened into a single array of dimension 1. Note, we can add or remove dimensions of size 1 using torch.unsqueeze or torch.squeeze. So here, create a tensor with shape 1, 3, 1, 4, and then I say tensor is equal to torch.rand, and then give it this shape. Squeeze tensor is equal to tensor, this tensor, dot squeeze, and then if we print this squeeze tensor dot shape, we're going to see that all dimensions with ones are removed. So if we have a torch with size 1, 3, 1, 4, and then we say, or tensor, and then we say tensor.squeeze, if we print that squeeze tensor, we're going to see that all dimensions where size is 1 are removed. So we have only 3 and 4, and 1 are removed with squeeze. And then unsqueeze is going to add dimension 1, a dimension of size 1 to this dimension that we specify. So first dimension with index 0, we're going to add a dimension that has size 1. We can also say a.unsqueeze minus 1. This will choose the last dimension. It's going to add 1 to the last dimension. Often the reshape does not require a physical copy of the data, but just a local reorganization. So it doesn't need to create a new tensor object. It can just reorganize that object. Given a rank 1 array of increasing numbers from 0 to 9 defined as a is equal to torch.arrange 10, use only the reshape and transpose functions to obtain the following tensor from A. It needs to be 0, 2, 4, 6, 8, 1, 3, 5, 7, 9. Take a look at this, try to solve it, and then I will show you the solution. This is the solution, so we're going to have this array, and then we're going to A is equal to a.reshape 5, 2, so we can get this kind of array, so 0, 1, 2, 3, and now, if you can see, it goes 0, 2, 4, so we have it 0, 2, 4, 6, 8, so we can just transpose now like this, and then we are going to get 0, 2, 4, 6, 8 into this dimension, and then we are going to just reshape this so it has 10 values. Or we can also say -1, so it's going to automatically calculate. Now let's learn about concatenation. PyTorch provides many functions to manipulate tensors. Two of the most common functions are torch.stack, concatenates a sequence of tensors along a new dimension, and torch.cat concatenates a sequence of tensors in the given dimension. So let's first try this out. A is equal to torch.arrange 12, and then reshape this to 3 times 4. So we have this matrix, and then we're going to do the same, but we're also going to add 100. So this is going to add 100 to each of the elements. And if we say out is equal to torch.cat, and we concatenate A and B tensors in the dimension 0, that means we are going to basically, this is the dimension 0, the outermost dimension. We are going to just merge all of the elements inside of these dimensions. So we're gonna just remove like this break and this break. We're gonna have like from here to here. So this is what we will have. We're gonna merge the outermost dimension, which is the dimension 0. We can also concatenate in dimension 1 right here. So you can see that in this case it's going to concatenate 0, 1, 2, 3, and then 100, 100, 100, 200, 3. So it's going to concatenate the first element here, the first array, with this array. And it's going to merge two of them. So you can basically see that this dimension will determine what gets merged, which dimensions get merged. And it's always going to start from this index. So the first element, and then second element with second element, etc. Now, if we use torch.stack A and B, it's basically going to take A and B and put them into another tensor. So it's going to put a wrapping tensor around both of them. Given a tensor with dimensions 3 times 1920 times 5 times 1080, reorganize it so you get the tensor 5 times 1925 times 1080 times 3. Think of X as a tensor that represents 5 RGB images, each one with 1920 and height 1080. Your goal is to reorganize this tensor in a sensible and useful way. So I'm going to show you the solution. You can pause the video first. This is the solution. A.transpose. So first, if we have this tensor, we need to have number 5 in the beginning. So we are going to swap dimension 3 and dimension 5. So index 0 and index 2 dimensions. And then we are going to have 3 here, but we want 3 to be at the end and 1080 to be on the third place. So we're going to swap index 2 and index 3. Transpose index 2 and index 3, and we are going to get our proper dimensions. You can also get the same result by using permute function. So a.permute, and then you're just going to say 2, 1, 3, 0. So you're going to have dimension 2 at the first place, dimension 1 at the second place, dimension 3 on the third place, and dimension 0 at the fourth place. Tensor indexing. There are multiple ways we can index tensors. One of the ways is the classic PyTorch indexing. So if we have this tensor A and we print A of 0, we're going to get the value that 0. If we print A of 1, we're going to get a value at index 1, which is 1. We can also print the last value, which is 9, and second to last value, which is 8. We also have multidimensional indexing. So if we reshape our tensor A to be 2 times 5, and this is our tensor, if we want to print the value at index 1, 3, it's going to be 8, because this has index 0, this has index 1, and then inside of this array, we're going to go to index 3, which is 8. If we say A of 0 is going to print the whole array, and then a of 1 is going to print the second array. We can also print index 0, so the first array, and the last element, which is 4. Exercise which element is 1 minus 1. So we're going to take, so when we look at this dimension, we take the number 1, index number 1 of the outer array, so it's going to be this whole array, and then the last index will be 9. Slicing, similar to Python sequences and NumPy arrays, PyTorch tensors can be easily sliced using the slice notation. So we can slice array by specifying start to stop. We can specify start, and it's going to slice array from start to the end, or from beginning to stop, or we can create a copy of the whole array. There is also an optional step value, which can be used with any of the above. So A, and then start, stop, step. Now let's see some examples. If we have array, if we have tensor A torch.arrange 10 plus 10, so we're going to go from 0 to 10, and then we're going to add 10 to each. We have this tensor, and then we are going to slice from 5 to 7 indices, but 7 is excluded. So 0, 1, 2, 3, 4, 5, so it's going to be 15, and number 6 is going to be 16, but 7 will be excluded, 17. And now we can make the array from the 5th last character to the end. So 15, 16, 17, 18, 19. Now we can go from beginning to end, but with step 2. So it's going to be 10, 12, 14, etc. With multidimensional tensors, we can perform multidimensional slicing. So if we have this tensor, we're going to slice it in the following way. So let's start from this one. This one means index number 1 in innermost arrays. So this has index number 1, this has index number 1. And then this is the outer array, so we're going to go from beginning to end in the outer array. So we're going to use both of them. So if I say this is going to produce this, because it's going to take index number 1, and then it's going to go all of them at index number 1. We can also go all of the arrays, all of the outer arrays, and then choose last numbers. So 4, 9. We're going to make that into an array. If we say -1, we're going to choose just the last row, this entire thing, and then we're going to go starting from third to last to the end. So this is third to last to the end. You can assign to slice tensors, therefore modifying the original tensor. Indexing and slicing operations do their best to return tensors that share the underlying data with the original tensor. So they do their best not to duplicate the tensor object, but to reference to the original tensor object when slicing. So let's say we define this tensor, and then we're going to define a tensor B, and let's start from the innermost dimension, because it's easier to explain and understand. So the inner dimensions are going to go from 1 to 3. So index 1 is here, index 3 is here, but 3 is excluded. So it's going to go from 1 to 2 basically. So it's going to be 1, this is 1, 2, and then 6, 7. And then which of these we want to add to our B tensor? Well, we want to add all of these that are inside of arrays with indexes from 0 to 2. So it's going to be both of them. This is index 1, and this is index, this is index 0, and this is index 1. We want to add both of them, and then inside of those we want to choose from 1 to 3. So 1 and 2, 1 and 2. That's why we have this and this. You should play with this, see what happens if you press 0 here. You're going to get 3 values, starting from 0 to 3. And now let's see what happens if we say the last row the last row, the entire thing from beginning to the end is minus 999. If we print this, we're going to say that the last row from beginning to the end is minus 999. And what's going to happen is the original tensor has been modified as well. This is because this B tensor is not copying the original tensor into itself, but is just referencing the original tensor. And then if we say in tensor A, the last row, the last column value is going to be minus 1. So the last row, the last column is going to be minus 1. Indexing with integers yields lower rank tensors. Let's define this same tensor again, and then we will say row underscore R1 is equal to A, and then we're going to say the second row, and we're going to give in all of the elements. And then if we print it, we're going to get, this is the second row with all of the elements. Rank 1 view of the second row of A, but then we'll also see rank 2 view of the second row of A. We're going to basically do the same thing, except instead of saying one dimension, we're going to say from 1 to 2, but excluding 2. This is going to yield the rank 2. So we have, this is the rank 1, and then the whole thing is rank 2. There is another way to get a rank 2 view of the second row of A. So if we say 1, but in an array, then we're also going to get rank 2 view. Same with the columns. And then if we say A, and then we go all of the rows, and then second column, we're going to get rank 1. But if we say all of the rows, but we want rank 2 view, we say 1 in an array, we're going to get rank 2 view of the columns. So in this case, it's going to just flatten the entire rank 2 view into rank 1 view. We can also create a slice object in Python. So if we say s1 is equal to slice, and then we pass in 3, this is equivalent to slice, and then it goes from 0 to index 3. As you can see, if we print this, it goes from the beginning, it's none, to 3, and then step is none, which means step is 1. If we print type of S1, we're going to see that slice is an inbuilt type. We have out is equal to A, and then passing S1 as index. This is equivalent to A, and then passing in this actual slice. Now let's define this string. We're going to say my string is equal to, this is just a string, and then we slice this with S1. It's going to just write the first 3 letters. We can also define S2 slice as slice none none minus 1, and then if we say my string S2, we are just going to go from the beginning to the end, but in reversed order. So if we actually try to do this in the PyTorch, PyTorch currently does not support negative steps, so it's going to throw an exception, and step must be greater than 0. So we can use negative steps on a Python string, but we cannot use it on PyTorch. We can also use something called integer array indexing. So if we have this tensor, we can create a new tensor in the following way. If we say A, and then we give it this array of arrays, what this is going to do is it's going to say indices of rows I want are 0, 1, 2. So the rows I want are 0, 1, 2, these 3 rows. And inside of those rows, I want index number 0, which is this one. And then I want index number 1, which is this one in the second row. And then index number 0, which is this one. So this is going to return 1, 4, 5. So it's 1, 4, 5. Index row 0, column 0, it's this one. Row 1, column 1, so it's this one. And then row 2, column 0, it's this one. This will be equivalent to if we just define 3 variables and then the first one is going to be a value of 0, 0, second is value of 1, 1, and the third is value of 2, 0. And then we just make a torch tensor of all three values, which is going to be this one. You can reuse the same element of the source tensor multiple times. So you can say, I want element from row 0, column 1, and after that I want element from row 0, column 1. So it's going to be the same element. The same thing is done here. You can use another tensor to perform indexing as long as they have data type torch int64. So let's say we have this tensor of ones. We're going to create a new tensor j that's going to be 0, 1, 0. So we have our tensor a that's going to be this tensor that we defined earlier. And then from this tensor, we're going to create a tensor out. And we're going to do this indexing. So we have I and j tensors. We're going to say, I want the following values from tensor A. So I, row number 1, column 0. So that's going to be row number 1, column 0 is going to be 3. This is the first element. Then I want row number 1, column 1. So this is going to be row number 1 and then column 1. So we have 4. And then I want row number 1 and column 0. So this is going to be 3. So we have 3, 4, 3. That's how we defined out using these two tensors. Exercise: change with a single assignment the elements of the tensor x belongs to 4 times 3 as follows. So we have this 4 times 3 tensor. How would you change all of these values in a single assignment? You can pause the video and now I will show you the solution. So first we're going to create a new torch tensor called values, and we will assign these values. So it's -1, 0, 1, 2. Then we will create row indices, and those are going to be 0, 1, 2, 3 right here. And we're going to create column indices tensor that's going to be 2, 1, 0, 1, 2, 1, 0, 1. And then use integer indexing to assign values to specific elements. So A, and then we're going to pass in this tensor, and then this tensor for the second dimension, and we're going to set these two values. And if we print A, we're going to just get the proper values that we changed. Another thing we can do is, let's say we have this tensor, and I can say, so I want rows from 0 to 3. So I want 0, 1, 2 rows, 0, 1, 2 rows, and each of them I want 0 to 3 columns. So it's going to be these 3 columns, these 3 columns, and these 3 columns. This is our new tensor that we get. Let's also check this out. So I want to display the following: row 0, column 0. So it's going to be this one, the value is 0. Then I want row 1, column 1. It's going to be this one. So the value is 5. And then I want row 2, column 2. So it's going to be, which one is it going to be? It's going to be this one. So the value is 10. We can actually write this exact thing using this method. So this is basically torch arrange 0 to 3. You're going to get this same array or tensor. And then torch arrange 0 to 3, you're going to get this same tensor. So you can write in either way. Now let's say I want rows from 0 to 5 with step 2. So those are going to be 0, 2. And then I want columns from 0 to 5 with step 2. So I want column 0 and column 2. So it's going to be 0, 2, 8, 10. 0, 2, 8, 10. Boolean array indexing. This type of indexing is used to select the elements of a tensor that satisfies some condition, similar to MATLAB's logical indexing. So if we have this tensor, we're going to create a classic Python matrix that's going to be called Boolean index. And we're just going to check if each element is greater than 2. So it's going to be false, 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 true, true, true. And now that I have this bool index, I can actually pass this to our A tensor. So if I say A bool index, we're going to display only values that correspond to true. So we're going to display this value, which is 3, and these two values, which are 4 and 5. 3, 4, 5. And they're going to be unrolled. Now we're going to see some graph use cases. So assume to have a weighted adjacency matrix for a non-directional graph, possibly with self-loops. We want to obtain the list of edges of this graph for which the weight is greater than 0.5. How can we do that? So first, let's define a random adjacency. So we're going to say A is equal to random integers. 5 times 5 is going to be to 2, so 0 and 1. We have this matrix of 0 and 1. And then if I say A.bool, it's going to change 1s to true and 0s to false. So then I just want to show you what this does. So if we add A and A transposed, we're going to get a symmetric matrix. This is going to be completely symmetric along the main diagonal. And then we're going to check for each element in this symmetric matrix if it's greater than 0.5. So this is greater, so it's true. This is greater, so it's true. And then, for example, this 0 is not greater than 0.5, so it's false. Let's see what this does. torch.random-like, and then A, and data type is torch.float. This will generate random numbers in the shape of A. So the same shape of A, but random numbers. And then what's funny is if you multiply this matrix and this matrix, true is seen as 1, and then false is seen as 0. So if you multiply true and this number is going to be this number because true is 1. But if you multiply false, false is going to multiply with this number at the same location, and because false is 0, this is going to become 0. So that's what we are doing right here. We are multiplying this, and if I multiply that, it's going to have values where we have true here, and then it's going to be zeros when there is false. Now the reason this number is different from this number is because these are all random numbers. We are generating random numbers. The point is we either retain random number or we set it to 0. After that, we are going to first check if these values are greater than 0.5 and also if they are not 0. So if they are greater than 0.5 and not 0, then we're going to get index of that value. And then we're going to return a tensor of all of those indices. So for example, index value at 0, 2 is going to be this value. This is both greater than 0.5 and non-zero. And then value at 0, 4 is going to be this value, which is greater than 0.5 and non-zero. So if we take a look at this row, we're going to have adjacent matrix with indexes of adjacent matrix greater than 0.5. So if you remember what this means, it's basically going to create like a Boolean mask. So everywhere where a value is greater than 0.5, it's going to be true. So for example, here this is greater than 0.5, it's going to be true, but these two are not, and those are going to be false. So we can actually use this to extract values from adjacent matrix as well. So if I say adjacent matrix and I pass in this mask that we just created, it's going to extract elements where the value here is true. So it's going to make a list of all of the elements where value is true. Now I didn't rerun it, so we had the previous numbers, but these are the corresponding numbers in our current matrix. So it's this value, and all of them that are greater than 0.5. Exercise: build a 3D tensor in X belongs to R 3 by 3 by 3 that has ones along 3D diagonal and zeros elsewhere, i.e. 3D identity. Now, I'm not going to give you the result because there are multiple ways to solve this. What I recommend you do is, if you don't know how to solve this, you copy this into ChatGPT and then you tell it, solve this using Boolean index, solve this using integer index, or solve this using for loop. And then compare different results and see how you can play around and understand how they work. And we have another exercise. Given a 3D tensor w times h times 3, representing a w times h image with RGB color channels, assume the color channel is the last dimension of the tensor and each color component. See. And there are also a few more exercises. You should try to solve them on your own, and you should ask ChatGPT. I will not show you the result because I want you to also learn how to use ChatGPT to solve these exercises and how to learn if you can't solve them yourself. This was Tensor Full Basics course. Thank you for watching, and check out my next course that's a continuation to this called Tensor Operations. Check out the useful links in the description below, and thank you for watching. See you in the next video.